The explosion of a shell. A 12-kilogram shell is launched at an angle of 55 degrees above the horizontal with an initial speed of 150 meters per second. At its highest point, the shell explodes into two fragments, one 3 times heavier than the other. So this is 3m, this is m. The two fragments reach the ground at the same time. Ignore air resistance. If the heavier fragment lands back at the point from which the shell was launched, where will the lighter fragment land and how much energy was released in the explosion? So we have an initial x component of the velocity vx0, 150 cosine 55 degrees, and we have an initial y component of the velocity 150 sine 55 degrees. And what happens at h max? At h max we have the same x component because there is no force on the x-axis, but the y component will decrease to 0 meters per second due to gravitational force. The explosion at this point is going to be sudden. It's a sudden explosion, and the gravitational force is going to be small, too small compared to internal forces. Therefore, we can neglect the effect of the gravitational force during the explosion. Therefore, we conclude that in the explosion process, linear momentum must be conserved. Okay, so if we write the conservation of linear momentum, delta px will be equal to 0. So that means the fragment with mass m times its velocity x component plus the fragment with mass 3m times its velocity x component should add up to the total mass 4m times Vx0, the initial linear momentum. So this gives us, here is a cancellation of the masses. So this gives us the following equation, Vmx plus 3v3mx must be equal to 4 times 150 times cosine 55 degrees. So let's label this equation number 1. The conservation of linear momentum on the y-axis, delta py is equal to 0, gives us m times vmy plus 3m times v3my is equal to 0. So this tells us that vmy is equal to minus 3 v3my. This is our second equation. Now, after the explosion, the time of flight delta Tf for the two fragments is the same. So they reach the ground at the same time. Okay, so the distance the fragment with mass m travels will be equal to Vmx times delta Tf, and the distance the 3m travels will be equal to v3mx delta tf. And because we have the same time of flight here, the distance traveled by m will be the ratio of the x components of the velocities vmx to v3mx times delta x 3m. This is the third equation. And at h max, we have the velocity as a function of y component as a function of time, which is going to be given as v0y minus gt is equal to 0 at h max. Therefore, the time to reach the h max is v0y over g, and delta x, the distance traveled during this time interval, will be v0x times t, which will be 150 cosine 55 times 150 sine 55 divided by g, which is 9.8 meters per second square. So this will give us 22,500 divided by 9.8 cosine 55 sine 55, which can be written as 11,250, because 2 sine theta cosine theta is sine 2 theta, divided by 9.8 sine 110 degrees. So that's the distance traveled on the x-axis to reach the h max. Okay. And after the explosion, for them to have the same time of flight, you can see that if Vmy and V3my are equal to 0, because we have Vmy, if one of them is 0, the other one will be automatically 0 due to equation 2. The distance traveled on the y-axis, delta y, which will be, if you write it as a displacement, that's minus h max equals minus 1 over 2 gt square. They will reach the ground at the same time. Or in other words, for them to be able to reach the ground at the same time, they must have y components of the velocity 0, according to equation 2, and according to the requirement that they reach the ground at the same time. So we obtain h max v0y v0yt minus 1/2 gt square. That's v0y. So the time to reach the maximum height was v0y over g. So v0y squared divided by g minus 1 over 2 gt squared, which is v0y squared over g squared. And this gives us, one of the g's cancel here, 1 over 2 v0y squared over g, which is equal to 1 over 2 g. So this t is what I have labeled delta tf, time of flight squared. They reach the ground at the same time. So this is 1 over 2 g delta tf squared, and therefore delta tf, the time of flight, is v0y divided by g. So we have basically used the fact that they have no initial y component after the explosion in order to reach the ground at the same time, and that means Hmax is 1/2 g delta Tf squared. But Hmax was also related to the initial y component of the shell when it was launched here. So it's this component. So V0yt minus 1/2 gt squared is Hmax. And with that, because the time to reach the maximum height was calculated to be V0y over g, that's where the y component of the velocity is 0, we substitute that here. So we find a relationship between the time of flight and the initial velocity y component and gravitational acceleration. So the distance traveled, the displacement on the displacement on the x-axis for the 3m is going to be equal to v3mx delta Tf. So let's say that this is going in negative direction. So this is basically minus delta x, which is minus 11,250 over 9.8 sine 110. So this is basically the same distance that the shell has traveled all the way up to the maximum point, because it's mentioned that the heavier fragment lands at the point from which the shell was launched. So delta x3m is the same distance as this shell traveled on the x-axis. So it is minus 11,250 over 9.8 sine 110, which is the velocity of 3mx component. So from equation 1, we have velocity of the 3mx component times the time of flight here, delta Tf, and the time of flight is related to V0y over g. So this is V3mx times 150 sine 55 over g, 9.8. So it is basically delta x3m is v3mx times delta Tf, but delta Tf is v0y over g, and v0y is 150 sine 55. Okay, so this gives us v3mx is equal to, because the g's cancel here, minus 150 cosine 55. So this is 2 sine 55 cosine 55. So let me write here, this is 2 sine 55 cosine 55. So sine 55 will cancel. So we will obtain minus 150 cosine 55, which is minus 86.0 meters per second. So it's equal to minus V0 x. And Vmx will be equal to 4 times 150 cosine 55 minus 3 times V3mx. So 4 times 150 cosine 55, because V3mx is negative, this is plus 3 times 150 cosine 55. So this will give us 7 times V0x as the x component of the fragment with mass, velocity of the fragment with mass m. So delta xm is Vmx times the time of flight. Vmx is 7 V0x. The time of flight is basically delta x3m divided by minus v0x, because the delta x3m is v3mx we found to be minus v0x, so time of flight is this divided by minus v0x, so this gives us 7 times 11,250 divided by 9.8 sine 110, and that is equal to 7,550 meters from the point of explosion. Okay, so this is where the mass with the fragment with mass m lands, or it is 8 times 11,250 over 9.8 sine 110, 8,630 meters from the origin. Okay, so we have found the distance from the origin. All right, so where will the lighter fragment land? So we have answered this question. And how much energy was released in the explosion? Initial kinetic energy of the shell is 1/2 4m 150 cosine 55 x component squared, because the y component is 0 at the maximum height. Final kinetic energy is 1/2 3m 150 cosine 55 square. It has the same x component of the velocity, plus 1/2 m. This one has 7 times the x component, 150 cosine 55 squared. So this is happening at h max. So that's the initial kinetic energy before the explosion. So this is after the explosion. So how much is the change in the kinetic energy? 1/2 3 times so it was a 12 kilogram shell, so 4m is 12 kilograms. 4m is 12, m is 3 kilograms. So 1/2 3 times 3, 150 cosine 55 square, plus 1/2 3 times 7, 150 cosine 55 square, minus 1/2 4m, which is 12 kilograms, 150 cosine 55 square. So this is our, again, kinetic energy at h max, initial kinetic energy at h max, and therefore delta k we find to be 9/2 150 square cosine 55 square, plus 3/2 150 square 7 cosine 55 square, minus 6 150 square cosine 55 square. So this gives us in 150 square parentheses 4.5 cosine 55 square, plus 73.5 cosine 55 square, minus 6 cosine 55 square, and this answer is 533 kilojoules. Okay, so it was a little bit long problem. So let's recap what we have done here. We have a 12 kilogram shell. So the total mass, I have 4m, so m is 3 kilograms, is basically exploding at its maximum height into two fragments, mass m and mass 3m. It was initially launched at 55 degrees angle with respect to the horizontal. So regarding the motion of this shell up to the maximum point, I know the following. The x component is a constant because gravitational acceleration is on the y-axis. So we have g on the y-axis. And the y component will be decreasing to 0 at the maximum height. And initial y component is initial speed cosine 55, initial x component, initial y component is sine 55, x component is 150 cosine 55. And I can, at the point of explosion, I can basically write the linear momentum conservation because there is an external force acting on this system, which is the gravitational force, but that is negligible compared to internal forces, and the explosion is sudden. So if I write the conservation of linear momentum during the explosion process, delta px is 0, delta py is 0. We have mvmx plus 3mv3mx is 4mvx 0. And m3vmy plus 3mv3my is equal to 0. So this gives us two equations. But at the same time, we have the information that the two fragments reach the ground at the same time. So if they had different y components of the velocities, for them to reach the ground at the same time, traveling the same distance would be impossible. So basically, h max is equal to 1/2 1/2 times g delta tf square equation is going to be satisfied only if they have initial y components to be 0. So that's one thing we learned from these two pieces of information. And after the explosion, the time of flight for the two fragments is the same, and the distance, the displacements on the x-axis, vmx times delta tf, v3mx times delta tf, and delta xm is related to delta x3m, vmx over v3mx. And regarding the time it takes for the shell to reach the maximum height, we have the final y component 0, so it takes v0y over g time. And the distance, because I have to calculate the distance I travel to reach the maximum height, that is v0x times t. And because that is the same distance, the 3m, the heavier fragment, ends up traveling. So this delta x is the same as delta x3m. Delta x3m, yes. So I find that they reach the ground at the same time, and h max is equal to v0yt minus 1/2 gt square. And the time of flight to reach the maximum height for the shell was v0y over g. So h max is related to v0y. It's 1/2 v0y square over g. It's at the same time 1/2 g delta tf square, because minus h max is the displacement of 3m and m to reach the ground on the y-axis. So I find that the time of flight is v0y over g. So delta x3m is basically minus delta x, which I have calculated here, 11,250 over 9.8 sine 110, the same distance the shell travels on the x-axis. And basically this is v3mx times the time of flight. So I find that v3mx is minus v0x. And because from this equation I have vmx plus v3mx is 4 times v0x, and if this is basically minus v0x, 4 plus 3, 7 v0x is the x component of the fragment with mass m. And delta xm, then the distance traveled by m with respect to this point of explosion will be Vmx times delta Tf. Vmx times delta Tf is 7 times delta x3m, which is 7,550. So this travels 7 times delta x3m. This is delta x3m. So the total distance between them is 8 times delta x3m, which is 8,630 meters from the origin where the shell was launched. Now we can calculate, knowing that we have no y components of the velocities for the two fragments after the explosion. We only have x components, which we have calculated in terms of v0x. One is minus v0x, the other one is 7v0x. We can calculate the final kinetic energy, and initial kinetic energy right before the explosion was 1/2 4mv0x squared. So we can calculate the change in the kinetic energy from this equation to be 533 kilojoules.